Alright, so let's talk about directional derivatives. Okay, here's the motivation for directional derivatives. If you have a function of two variables x and y, then so far we defined what it means to differentiate in the x direction, which is given by this limit h going to 0 of f of x plus h y minus fxy divided by h. And then I also said that if you want to differentiate in the y direction, you would place plus h instead in the y side, right? Okay, then you can be further creative in doing this derivative and say, well, this is like measuring the change of f as you're going in the x direction. So suppose this point is x comma y. What you're doing is, if you go h to the right, this point is x plus h comma y. Say this is x, this is y. And you're trying to find the change of f between these 2 points, right? So this can be thought as the rate of change of the function as you're moving in the x direction. That's what partial with respect to f means. And then if it was partial with respect to y, you would be going upwards. Then after seeing this on this graph, so by the way, it's really a slope. This is like the slope of the tangent line, right? So if you have the function f, the graph of z equal to fxy actually resides in this three-dimensional space. So over each point, you have the value of the function over it, right? And then as you move from point to point, the altitude of the function f, the z coordinate, it changes, right? And you're trying to divide the change of f with respect to this length h. So if it was like, if the function value was here and then over here the function value was here, then there's this difference in the function values divided by this length h, and that's the slope between the 2 points. And then when you close this h gap into 0, then you get the instantaneous rate of change at that point, or the slope of the tangent line. And then you can do the same thing in the y direction. Now, once you have this picture understood, then the natural question that you can have is, what about other directions? What if you decide to measure how f changes in a direction other than x or y? Suppose you have this angle theta, and you want to know how the value of the function changes from this point to that point as you move along this way. Okay? Now we can write down the formula for the rate of change of this. And by the way, usually the formula is written in the following way. If you call this vector as u hat, the rate of change of the function f as you go along this direction is called round f round u, okay. Round f round u of xy. And it's defined in the following way. Because u is really it's a vector. Let's call this a and b in 2 dimensions. Then you want to move h length in this direction. So if you do h times u, then it becomes a length h vector, because u hat is a unit vector. So if you multiply by h, the length shrinks down to h, right? So if you multiply by h, these are the increments in the x and y that you want to give, and you need to do the following limit. You want to do f of x plus ah, comma y plus bh minus f of xy over h, and you're taking limit h goes to 0. So that's what direction. This one is called a directional derivative. The title for this derivative is called a directional derivative. Now, sometimes people use the following notation for directional derivative. They use d, capital D, u hat f. Okay. So that's another notation for the directional derivative. There are two different notations for the directional derivative. They're used some books use both. Some books stick to one. Some books stick to one of them, but you have to know both, because they're both used widely. So this is called the directional derivative. Okay, now let's try to actually find the limit using L'Hopital's rule. Now, you don't have L'Hopital's rule for multivariable functions. However, this could be thought as a single variable function on top, because x, a, b, x, y, all these are fixed values, so you can really think of the top and bottom as function of h, in which case you can use the regular L'Hopital's rule. Let's apply the L'Hopital's rule. So what we need is to first verify that this is 0 over 0 type limit when h is taken to be 0. If you plug in 0 into the denominator, you get 0. If you plug in h equal to 0 on top, what do you get? You get 0 here, 0 there, so you have f of x comma y minus f of x comma y. What's that? That's 0, right? So you have this is a 0 over 0 type indeterminate. Therefore, you're allowed to use the L'Hopital's rule. You know that L'Hopital's rule can only be applied when you have 0 over 0 type or infinity over infinity type. So let's differentiate. Now the derivative of the bottom is easy. What's that? 1. Right. So the only thing that you have to be careful about is the top one. How do you differentiate this? Now, we're trying to differentiate this with respect to h. So the question is, what is the derivative of the top with respect to h? F of x plus ah, y plus bh, minus f of x. Now, the easier part is the derivative of this one. What's the derivative of f of xy?
F of x, y.
Yeah, f of x comma y differentiated with respect to h. What's that?
0.
0. Because this doesn't have any h in it. As I said, we're just going to consider every x, y, a, b, all of them as fixed values, constants. And you're treating the entire thing as a function of h, right? So because there's no h in here, if you differentiate this, you get 0. That goes away. Now, this one we have to think a little bit, because it's really like this. It's a little confusing because instead of x, you have x plus ah. So think about it like this. Let's say u is equal to x plus ah, and v is equal to y plus bh. then we have the following dependence diagram. F depends on u and v, because u and v are both in here and there. That's u and that's v. So f is a function that depends on u and also in v, right? And then u and v depends on what?
X.
No, I said x and y. H. These are all functions of h, right? X, y, a, b, we're just going to consider them as constants for this discussion, right? And therefore, we can use the chain rule, the multivariable chain rule, right? How does that work? You first differentiate f with respect to the first component, right? So f differentiated with respect to u times the derivative of this with respect to h plus f differentiated with respect to the second component v, this one, times dv dh. That's what I said, right? Now what is du dh?
A.
Yeah. If you differentiate x plus ah by h, what do you get? Just a, because x differentiates to 0, and ah, if you differentiate, it's just a, right? So that's a. And then the second one is b. So that's the formula. Now, however, this is not the formula we want to use. This is what we're going to use in general. In general, if you're given f of x comma y with the vector u, and usually if you're in two dimensions, and if this is angle theta, then you can actually write down the vector u as what? Cosine theta comma sine theta, right? So instead of a and b, we can use that. Also, notice that when we wrote down round f round u, we really meant differentiation with respect to the first component, first part, right? So in this, I can translate this over to this context and say instead of round f round u, we can just say f differentiated by the first component, in which case this is our x, okay? And times cosine of theta plus round f differentiated with the second component, in this context is round y, times b, and for rb it's sine theta. So that is the formula that we will temporarily be using for our directional derivative. Okay? So the directional derivative is d u x. That's a temporary formula we'll use. I'm saying it's temporary because soon I'm going to introduce to you gradients, and using gradients you can represent the directional derivative in a much easier way. Okay, but for now, this is what we are going to say. If you want to know how fast f is changing in the direction of angle theta, then you take the f partial with respect to x, multiply by cosine theta, f partial with respect to y, and multiply by sine theta, and that's your directional derivative. Now let me show you with an explicit example so that you can understand this formula better. So, example, let f of xy equal to x squared plus 3x. Find duf duf for the unit vector -1/2, radical 3/2. what is that? That's like this direction, 120 degrees, right? At the point 2, comma 1. So this is what we're asking. Here's on the x and y, on the xy plane, here's 2, comma 1. Here's this point. And the question we're asking is, if we move along this line, this direction, what is the rate of change of f? That's basically the question. Okay? And the solution is like this. For now, temporarily, we'll be using this formula, but as I tell you, we're going to use a better formula next time, a simpler one. But for now, this is what we have to do. First, we have to find the partial with respect to x, which is, what's that? If I do partial derivative with respect to x.
2x.
2x plus
3y.
3y. Now, if you evaluate this at 2, comma 1, what do you get?
4 plus 3. So
Right. This means x is 2 and y is 1, right? So that's 4 plus 3. Because if x is 2, 2 times 2 is 4. Well, if y is 1, 1 times 3 is 3. So you get 7. And then, if you find round f round y, what's that? What's the partial with respect to y?
3x.
It's just 3x, right? So what is round f, round y, evaluated at 2, comma 1? 6. It's just 3 times 2. So 6. And then, now what you have to do, you say duf, evaluated at 2, comma 1, is 7 times what?
Cosine theta.
Cosine theta, which is negative 1/2, right? Plus 6 times radical 3 over 2, which is negative 7 over 2 minus 3 radical 3 plus. Okay? So that's how you compute the rate of change as you move along this line. Now, let me show you another way of thinking about this to further let you understand what's going on. So think about this line. Think about a moving particle. Yes?
So you plug negative 1 over 2 or radical 3 over 2 in for theta.
No, I plug in, see, these are really, this is really cosine of 120 degrees, comma, sine of 120 degrees, right?
Oh, okay.
Yeah. So cosine 120, cosine theta is negative 1/2, and sine 120 is radical 3 over 2. That's what I meant. Okay? All right. So by the way, sometimes I might give you theta, and then in that case you have to compute the cosine theta, sine theta to use that formula I just erased. Okay? Now, to give you a further understanding of what's going on, think about this particle that's moving on this line. Okay, so starting at 2 and 1, and then you're moving at the velocity of negative 1/2, comma, radical 3 over 2. So that's a particle that's starting at 2, comma 1 when t is equal to 0, right? If you differentiate it, you know that the velocity of this moving particle is negative 1/2, comma, radical 3 over 2. Because if you differentiate this, this goes away, and if you differentiate t, that's 1, so that's what you get, right? So if you differentiate each one of them, you get this velocity vector, negative 1/2, comma, radical 3 over 2, which is exactly this one, right? Now the question is, I want to know how fast this quantity changes when time changes. Okay? So really, this is what I'm doing. I'm trying to do, what is the rate of change of f as I move along this curve. Now, in order to do that, I need to plug all these here. So at each point I have to evaluate the value of f, because I want to know how fast this value changes. So let's first plug these into here and there. What's that? That's 2 minus 1/2 t, that's x, that's squared, plus 3 times 2 minus 1/2 t times 1 plus radical 3 over 2t. This is x, that's y, right? And this is the entire f. You see it? All I did was I replaced this x by what I have here. I replaced y by what I have here, so that at each moment in time t, this is the value of f. And what I'm trying to do is I want to see how fast it's changing with respect to time. Now, let's see what we get. We can actually differentiate this just using calculus 1 knowledge, right? This you need to use the chain rule, 2 times 2 minus 1/2 t times the derivative of the inside function, which is negative 1/2, right? This one you need to use the product rule, which is 3 times, if I differentiate, this is negative 1/2, 1 plus radical 3 over 2t. And then plus, now I have to differentiate the second one, which is 3 times 2 minus 1/2 t times radical 3 over 2. Okay. Now what do? Well, this represents the rate of change of function at each moment in time, right? But really what we computed here is the rate of change at this point, right? At this point right here. Okay? And because of that, in order to get the same answer as this one, what we need to do is we have to evaluate this at time t equal to 0. Okay, so you plug in t equal to 0. Let's see what we get. In that case, this is 2 times negative 1/2. And then 3 times negative 1/2 plus, I can multiply it, right? So the first one is this times 1, which is just itself. This times this. Oh, and then, by the way, if t is 0, that's just gone, right? So it's just 3 times negative 1 times 1 for the second one. And then if I plug in t equal to 0, I get plus 3 times 2 times radical 3 over 2. They cancel, I get plus 3 radical 3, just like what I have there, right? And then I have 4 times negative 4 over 2 minus 3 over 2. They add up to negative 7 over 2, right? So I get the same exact answer. Okay. So you can say that this way will be a roundabout way to get the same answer. If you wanted to know the directional derivative and you totally forgot what formula to use, then a roundabout way to get the same answer would be using this. You make a particle that's moving on this trajectory, find the derivative of the function along this trajectory, and set t equal to 0. You get the same exact answer. Do you have any questions? Does this make sense?